In this short video, we're going to look at kinetics for AS chemistry. You will be aware of some of this idea of kinetics or rates of reaction from GCSE. The main thrust of this talk will be around the Boltzmann distribution, which is nicely shown here. Okay, but before we do that, let's go back to something that you do know. Okay, so you know that you can increase the rate of a chemical reaction by a number of ways. The first of these is by increasing the concentration of a reaction. So, if you have a reaction with a low particle concentration, and then if you increase the concentration, so have double the amount of particles inside your container of fixed volume, then you're going to have more particles per unit volume, and therefore there are going to be more collisions per second, and this will lead to a greater frequency of collisions with an energy greater than the activation energy. Similarly, the effect of pressure. Now, the pressure only applies to gases, and so it's the same as the effect of concentration on a solution. So increasing the pressure, this means that you've got the same number of particles but in a reduced volume. So just imagine halving the capacity of this rectangle. And therefore you would have more particles per unit volume because you've got a lower volume. And again, there would be more collisions per unit per second, and this would lead to a greater frequency of collisions having an energy greater than the activation energy. Okay. Also, you know about catalysts. The one catalyst you probably know already is iron in the Haber process. But catalysts, and also enzymes as a biological catalyst. Okay, now a catalyst is very important, especially in terms of industry. And what a catalyst does, it provides an alternative reaction route with a lower activation energy. So if you look at the enthalpy profile diagram here for an exothermic reaction, your uncatalyzed reaction is shown here in the black line, and the activation energy for that uncatalyzed reaction is this green arrow here. A catalyzed reaction has a lower activation energy, so that's represented by this red line here, and the activation energy here for the catalyzed reaction is lower. Okay. Note that the enthalpy change is exactly the same for both the catalyzed and uncatalyzed routes. Similarly, for the endothermic reaction, the activation energy for the uncatalyzed reaction is shown with this green arrow here, and the enthalpy change for the catalyzed reaction is shown with the red arrow here. And we can see that even though the activation energy is still high, it is smaller than that for the uncatalyzed reaction. Again, the enthalpy change is the same for the for this reaction. Okay. So, catalysts in industry. Catalysts in industry are very important. Many processes rely on them to reduce the costs, and also makes processes more environmentally friendly. Mainly is that catalysts allow reactions to occur at lower temperatures and pressures, and therefore there's lower fuel or lower electricity costs. Okay. If you've got lower electricity costs, then that's beneficial financially, but also less carbon dioxide will be generated, which is a greenhouse gas, because the energy required, because the electricity will be made by burning fossil fuels. usually. Okay, catalysts can also be used again. They can be recycled, and they can also lead to an increase in the percentage yield of a reaction. Biological catalysts are enzymes, and these are brilliant because they are catalyze specific reactions to form specific products, and there's no side reactions. So this means there's a better atom economy and there is less waste produced. Okay. Another main advantage of these enzymes is that they are biodegradable, so you can usually boil them up in a bit of dilute acid, dilute base, and then they can be flushed down the sink. So that's a benefit, whereas conventional catalysts, which are based on metals in these four processes here, then these are generally toxic. Okay, so the main bit, the Boltzmann distribution. The Boltzmann distribution is a qualitative way of describing how the distribution of energies of molecules at a particular temperature can be represented. So here's a basic version of the Boltzmann distribution here. Okay, so the important parts are here. The area under the curve represents the total number of particles, or the total number of molecules involved in this reaction. The curve always starts at the origin because no particles have zero energy. Yeah, so all particles, all molecules are vibrating and stop moving when you're at absolute zero. The highest point on the graph is the most probable energy. And this means that the most molecules will have this energy. This peak, this line here, just to the right of the most probable energy, is the average or the mean energy. Okay, this is different to the most probable energy. Most probable energy is the mode. This is the mean. Okay, so fewer molecules have the average energy. Also, if you look at this line here, it doesn't touch the origin again. It doesn't touch the horizontal axes, because we're saying there's no limit to the energy a particle could have. And finally, the important bit is here. Only molecules with an energy greater than the activation energy, shown here, will have sufficient energy to react when they collide. Okay, so all of these points are labelled up here on your diagram. So we can use a Boltzmann distribution to explain the effect of temperature on a reaction. So here we've got two lines. The blue line is at a lower temperature, the red line is at a higher temperature. What we see here is that the blue line is our basic curve. The red line now, when the reaction is at a higher temperature, is smaller in height, but it doesn't come down as steeply after the most probable energy. And this indicates that we've still got the same number of molecules and the same number of particles as we have underneath the blue line. Also, the activation energy does not change in this reaction, in this profile. And so we can explain that a higher temperature leads to a higher rate of reaction because there are more molecules with an energy greater than the activation energy. So therefore there are going to be more successful collisions and which will lead to a faster rate of reaction. If we look at the effect of adding a catalyst, okay, now here we've got just one line, which is our basic curve, and what we see is that we have a faster rate of reaction because the activation energy has now been lowered. And so this squiggle here represents the amount of molecules which have an energy greater than the activation energy, and which can lead to a successful reaction when they collide. The important thing is here is that we have more molecules with an energy greater than the activation energy, so that's why the rate of reaction is increased. Okay, so now it's your turn to have a go at trying to sketch these diagrams. So when you look at this question, draw a label Boltzmann diagram for a sample at 20 degrees. Include the activation energy on your sketch. So think of this as the blue curve on the the blue curve on this Boltzmann diagram. For this one, again, draw a Boltzmann distribution and include a second curve with a much lower for a reaction, a much lower temperature. Okay, think about what could happen, because it's going to be the opposite effect of having a higher temperature. So having a lower temperature, we're going to have our peak is going to be higher, and it's going to be shifted to the left hand side. Okay, and that's the end of this video.